Yesterday, we started building parametric curves in R3. We want to be able to describe a one-dimensional set in R3. We've described solids in a triple integral. We've described surfaces with equations or functions. And we want to start describing one-dimensional things. We can do the three-dimensional things. We can do the two-dimensional things. Now we need to be able to describe one-dimensional things in three-dimensional space. And we're going to do this by writing parametric equations or parametric curves. We're going to do this by parameterizing the curve. So if you would recall, if we have a linear equation in three variables, that will give us a plane which is two-dimensional in R3. So the equation a times x minus x naught plus b times y minus y naught and so on. That's got to be a plane containing the point x naught, y naught, z naught with normal vector a, b, c. So it's everything perpendicular to the vector a, b, c. When we write a linear equation in three variables, we get a two-dimensional plane in R3. We want to be able to describe a one-dimensional line in R3. So we need something else to describe a line. So lines are very simple things. Lines in any space just need a point and a direction. A line consists of a point and a direction. A line only ever needs two things, a point and a direction. Way back when we first started studying lines, back in the halcyon days of elementary algebra, when we were teenagers, and we didn't know anything, so that meant we knew everything. We described that direction with a slope, rise over run. But now that we're in R3, we're in three-dimensional space, we're going to have to abandon slope in favor of vectors. So we're going to need a point, a fixed location, and a vector. So a point is a fixed location. And we're going to need a direction. In R2, we used slope. We used slope for a very long time. We used slope for a long time, but now we've got x, y, and z. So for the direction, we were able to use slope for a long time. In R2, changing y divided by changing x. But now we have x, y, and z, so we need something else. And that's why we have vectors. Our strategy for forming the equation of a line is going to be the same. Start here, go that direction. Our strategy is going to be the same. If we think back to our original formulation of a line in slope-intercept form, we write y equals b plus mx. And we say start here. It's a little suspicious to say start when the line goes on forever in both directions. So let's say start here. And go this direction. Y is b when x is 0, and we add m a bunch of times. B is the fixed location, has no variable part to it. M is what we add a bunch of times. So start at B, add M a bunch of times. We start with B and we add M a bunch of times. That bunch of times is the X. Here's our fixed B with no variable. Here we are adding M, and here the number X is the number of times we add M. This is how we build a line. All we need is two things: a starting point and a direction, a place to go to start and a direction to go. This is how we formulate that. When we only had two variables, we could say start y at this value and then add m a bunch of times. We are going to employ the same strategy when it comes to building a line in R3. Our direction is going to be described as a vector. We're actually eventually going to describe the whole thing as a vector like we did yesterday. So our strategy is going to be the same. Let's build a line in R3 that goes through the point x naught, y naught, z naught, and follows a direction of some vector. I keep hesitating because I think I'm going to just use this as the direction, but I don't know if it's fine. It's fine. It's fine. This is a plane. This is a normal vector, not a direction vector. So we're going to do the same strategy when we describe a line in R3. But when we say start here, that starting point needs to be a location in R3. So our starting location is going to be a point in R3, x naught, y naught, z naught. Then we're going to add a direction vector a bunch of times. So then we're going to add a direction vector a bunch of times. Now I want to add this vector A, B, C gets multiplied by the scalar t. That's the number of times we add that vector. And to make this addition work, I got to think of my starting location as a vector as well. So we're going to think of this as a vector. This is the same construction that we had. This is the new version of y equals b plus mx. Start at the location x naught, y naught, z naught. That is a fixed position. There's no variable attached to it. And then we add our direction a bunch of times. Where t is the bunch of times we add this vector. So x naught, y naught, z naught, this is like our starting position. It is fixed. It's not going to change with the value of t. A, B, C is the direction of the line. That's the one that we add a bunch of times. If we draw a picture of this, we have some starting points. Well, we have the origin. And then we have some starting points that we're imagining as a position vector. And then from that point, we go in the direction ABC a bunch of times. We add the ABC a bunch of times, so I have it add it twice. And then 3 times. And then -1 times. Then -2 times, and so on. So we get this line. Once ABC is fixed, I could start this in different locations. So if I change the values of x naught, y naught, and z naught, I will get a line parallel to this one. I would start in a different location, but I would get a line parallel. So parallel lines will have the same direction vector, just like parallel lines have the same slope. Because when we say parallel lines have the same slope, we're saying that they go in the same direction. We're just rephrasing what direction means. So instead of slope, we're describing the direction with the vector. Parallel lines will have the same slope, but as we know, perpendicular to this line in R3 will be an entire plane. There's a whole plane perpendicular to this line. So we want to note that parallel lines have the same slope. Parallel lines have the same slope, just different starting locations. It's sus for me to say start because the line goes forever in both directions, but parallel lines have the same slope. It's also weird for me to say slope, but I mean direction vector, same direction. In R2, when we draw a line, we can draw a line perpendicular to a given line. In R2, a line is perpendicular to a line. But in R3, we have a whole plane perpendicular. This is how we get away with describing a plane with a normal vector. Direction vector of the line is the normal vector to the plane. So here is a vector form of describing a line. So here we have a parametric vector form of a line. Any questions? Realized I had my volume down. People in Zoom could have been asking me questions, and I just seem like I'm ignoring them. Now that the volume is up, I won't seem like I'm ignoring you. I'll be actively ignoring you. I'm just kidding. Now, we did talk a lot about elementary algebra stuff when we talked about lines, but this is because we want to talk about the thinking of a line. I think a lot of times we get into this when we're dealing with things like our algebra knowledge. We kind of get through algebra and we let that thinking stagnate, and we don't kind of bring up this kind of thinking every time it comes up. Mostly because humans, when they hear stuff they already know, tend to be like, oh, yeah, I know this. And then I give people a quiz on lines, phrase things slightly differently, and everybody flunks. And so I'm like, oh, but did you know, really? But that's okay. That's why it's part of philosophy to just say the obvious thing. Draw the obvious parallel. Because what's obvious to me is not going to be obvious to everybody in the room. So once again, a line is just a point and a direction, a location and a direction. Those are the only two things we ever need to draw a line. We can write, although we like to write these in parametric vector form, if I write these vectors together, so here's our parametric vector form. we can get the parametric equations by just writing these, by just adding these two vectors. So if I add these vectors up, I have x not, this is just a linear combination. So I multiply by t. I have this first component will be x naught plus a times t. Our second component will be y naught plus b times t. And our third component will be z naught plus c times t. So we can just put this together, and now we can write the parametric equations. X is a function of t. Is just x naught plus a times t. Y as a function of t is just this linear equation, y naught plus b times t. And z is a function of t is z naught plus c times t. Remember, the upside down a is the abbreviation for all. So that would say for all t. Another way to say for all t, since t is a scalar, and since we use the real numbers for the scalars, we could say, or we might say t is real, or we might say t is from the set from negative infinity to infinity. Or we could restrict our values of t. So we've got a parametric vector form, and we've got our parametric equations. Questions? We care about this because one of the things that we care about are tangent lines. This is calculus class after all, and we want to be able to write the equation of the line tangent to a curve at a given point. That's in R2. We did that in Calc 1. Now that we're in R3, we have to describe curves parametrically. We have to describe tangent lines parametrically. Notice that a lot of similar things happen. So if I write y is just b plus m times x, then y prime is just m. A linear function has a constant rate of change. And I'm specifically thinking of this as the derivative of y with respect to t. So if I have the vector form of a line, the same thing happens. R prime of t, the derivative of this constant is equal to 0. The derivative of something times t to the first power is that thing times t to the 0 power. And this would be the derivative of r with respect to t. If we're going to call something something, it should behave the same way. That's why we have words. This is why I like math, because words have meaning. And that meaning is way more consistent than just in English. Question? I'm sorry, say that again? Oh, it's not a prime, it's t to the first power. And then when we take the derivative, it's like t to the 0 power. Just like this is x to the first power, and this is mx to the 0 power. I was just highlighting the derivative of a linear function is constant. Just saying things, same slope. English is terrible. Words just like change their meaning all the time. I guess not all the time. But it's kind of like this continuous change. As people that are roughly 30 years apart in age or more, 35 years apart in age, anyway, 3 decades apart in age, there are words that I grew up with that we don't say anymore. There are words that I grew up with that probably mean something entirely different to you. Even though we all speak the same language, some of our words mean different things. By the way, this is a feature, not a bug. It would be weird if young people talk just like the old people. Just like it's weird when old people try to talk like young people. It's just kind of embarrassing. Just keep using the language that you used in your youth, and you'll be fine. Everything will be groovy. I'm just kidding. Groovy was old by the time I was a child. Made a bit of a comeback because of the Evil Dead movies, but that's beside the point. So we have equations of lines. They look the same as equations of lines did before, but they look slightly different. The structure is the same, but they look different because we have a lot. It seems that there's a lot more going on. All we have to do is remember that a line is just a starting point and a direction, a location and a direction. We can describe the line in this parametric vector form where we think of this first vector as a fixed vector. And then here is where our direction is, just like we think of the fixed point 0, comma b, and the slope rise over run, describing the slope with rise over run. One thing to keep in mind, a line in R3, parallel lines will have the same direction, the same ABC, but perpendicular to a line in R3, as we know, will be an entire plane. One of the things that we have to do way back in algebra is, given 2 points, find the equation of a line. And we start that problem off by finding the slope, change in y divided by change in x. We do exactly the same thing if the line is in R3. If I say there's a line if we have a line that contains the points 1, 2, -3, and the point 3, 5, 4. I was going to put a period here, but that's not a whole sentence. I'm just saying line contains this point and that point. I guess it kind of is. It's a terrible sentence. I didn't capitalize anyway. We do same thing that we did way back in elementary algebra. Take 2 points, find the slope. In this case, we're not finding slope, change in y divided by change in x. We're finding a direction vector. So our direction vector v is going to be 3 minus 1, 5 minus 2, 4 minus a -3. Just look at how much the x changes, how much the y changes, and how much the z changes from one point to the next. In parametric equations, I would want to describe an x, a y, and a z. So x of t could be 1 plus 2t. Y of t could be 2 plus 3t. And z of t could be -3 plus 7t. If I want the line segment that starts at this point 1, 2, -3 and ends at 3, 5, 4, I will say just do this for t from 0 to 1. When t equals 0, we'll be at the point 1, 2, -3. And when t is equal to 1, we'll be at the point 3, 5, 4. If I want the entire line, I just say for all t. We might be concerned that we wrote the points down in the opposite order. If we write the points down in opposite order, what's opposite of blue? Is it orange? So maybe we looked at the problem and we wrote the problem down, the points down in opposite order, and we wrote this other v. And I wrote 1 minus 3, and then 2 minus 5, and -3 minus 4. It's okay, we're just describing the line going in the other direction. same line. This is just the opposite direction of our original direction vector. So if we build a line, we could start at the second point at 0 and then head towards the first point. We're still drawing the same line. Just like when a slope is, let's say, -3/4, we can read this as -3/4 or 3/-4. When we have a slope of -3/4, we could read that as down 3, right 4, or up 3, left 4. We will still be drawing the same line. So if I go down 3 and right 4, that's the same line as if we go up 3 and left 4. Question? Lines, they work just like we expect them to. You just have to get used to the notation. All right, that's going to do it for this part. That's going to do it for describing parametric curves. I know we've only talked about essentially 2 parametric curves. And that's okay. Now we're in the practice phase. We understand the idea behind what we want to do and how we're going to do it. We're going to describe the x, y, and z as functions of some parameter t. And that way we can describe a one-dimensional curve in 3-dimensional space. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.